We're going to now look at two tests for absolute convergence that are related. They're tests that are generally used when we're dealing with series that look like p-series or look like geometric series, but they're not exactly in that form. And this first theorem is called the direct comparison theorem. And so we're going to look at two series here. Okay, I'll call this first series A and call this second series B. And these terms are all going to be non-negative in both of these series. Okay. And this theorem says the following. It says that if the B series converges and all of the terms in the A series are less than the corresponding terms in the B series, then the A series has to converge. And the reason why this is true, if we think about this for a second, let's look at the nth partial sum for A. Okay, because all of the A terms are less than the corresponding B terms, it's going to be bounded above by the nth partial sum for B, which is itself bounded above by the limit of the sequence, which is equal to the value of the series. Okay, so if this converges, if this is a real number, notice that the the sequence of partial sums are an increasing sequence, and they're bounded above by some number. Okay, so if we let beta, if we consider a real number line here, this may be the first partial sum for A, the second partial sum, and now we're going to use this result that we talked about before, the least upper bound theorem. It says that if a sequence is bounded above, then the sequence has a least upper bound. And that least upper bound is the value that the sequence is going to converge to. Okay, so by the least upper bound theorem, this theorem is true. And notice that if conversely the B series diverges and every term in the A series is greater than the corresponding term in the B series, then the A series has to diverge. And the reason why is because if we look at the partial sums now, okay, the partial sum for B is always going to be less than or equal to the partial sum for A. And since this diverges to infinity, okay, then it also has to be true that the A series also has to diverge to infinity too. Okay? And I want to give you some examples of when we can use this. So there's kind of some details as to when we use the limit comparison and when we use the ratio comparison test. So let's look at the limit comparison test first. I'm sorry, the direct comparison test first. Okay. One second. Let me get rid of this mark here. Okay, so let's look at an example where maybe we have something like, let's say, let's look at this series first, where we're going to have a summation from n equal 1 to infinity of 1 over 5 times the square root of n minus 1. Okay. Now, we should notice that this part right here looks like a p-series. Okay. We don't actually care about the 5. We're going to deal with that, but we're not going to care about that just for the moment. So this suggests that we should try a direct comparison test. So here's what we're going to do. We're going to compare this to we want to compare it to the series 1 over the square root of n. And I'm going to actually make this 1 over 5 square root of n. Okay. And we know that this diverges because this is a p-series where p is less than 1. And if we compare the series terms, we notice now that 5 times the square root of n minus 1, this is our an here, right? This is greater than bn. So by the direct comparison test, we know that this series diverges. Also, let's look at another example where we can use this result. So let's look at a series maybe like this. And again, we're going to look at the leading term. So this we're going to compare to the p series for p equal to 2. Okay. And we know that this series converges. And we also know that the an is less than the bn here. So we know this is true, and we know that the an, which in our case is n squared plus 5n plus 3, is less than the bn. So this tells us that this is going to converge. So this implies, by the direct comparison test, that our original series is going to converge. Converges. Okay, so it's a very useful theorem. Now, there are times when we'll have something very similar to this, and in fact I'll give you variations of these exact examples where we cannot use the direct comparison test because the inequality goes the wrong way. And let me show you what I mean. And in that case, we're going to use this thing called the limit comparison test. And the limit comparison test basically says the following. It says that we're looking at the asymptotic terms in the sequence. We're going to compare the asymptotic terms in our series to the asymptotic terms in a series whose behavior we know. Okay, so here what we're really doing is we're comparing the asymptotic terms in our series with those of a series whose convergence we know about. Whose convergence or divergence we know. And so this theorem says the following. If we have an A series and a B series, and now the terms all have to be positive, if the limit of the ratio of the terms in those series, an over bn, is equal to a positive constant, then either both converge or both diverge. Okay? But if the limit of that ratio goes to 0 and the B series converges, then the A series has to converge. And this is kind of obvious in the sense that if you think about it, what this is saying is, this is saying that in order for the limit of the ratio to go to 0, eventually the limit has to get less than 1. So this means after some n, an over bn is less than 1, which tells us that an is less than bn. Okay, and so actually by the direct comparison, although we have to do a little bit of work, the direct comparison test suggests that if this converges, then this series has to converge also. Okay? But if the limit of the ratio goes to infinity and the B series diverges, the A series has to diverge. And again, this makes sense. If the B series is diverging and this ratio is going to infinity, it means that the AN terms are growing faster than the B terms. And so if the B series goes to infinity, then it has to be the case that the A series goes to infinity. Okay. And if you look at part B of the theorem, this is kind of saying the same thing. It's saying that the A terms grow slower than the B terms. And so if B converges, then A has to converge. Let me show you some examples of when we'd have to use the limit comparison test. So here's an example using a P series, and I'll show you one with a geometric series. So let's look at this series. I'm going to call this my A series. Now, I want to compare this to the P series for P equal 1/2. So I want to use this as my B series. Okay. I know that this diverges, right? But notice that the inequality is going the wrong way. So if we try to use the direct comparison test, we can't. Because a direct comparison test requires an to be greater than or equal to bn. And we don't have that. This is not true. Okay, if you look at this, 1 over 1 plus the square root of n is going to be less than 1 over the square root of n. In other words, an is actually less than bn. So we can't use a direct comparison test, but we can compare the asymptotic properties. We can use a limit comparison test quite easily. So instead, we use a limit comparison test. So it says, okay, let's look at the limit as n goes to infinity of an over bn, which is equal to the limit as n goes to infinity of the square root of n over the square root of n plus 1. And we can show using our tests for sequences using L'Hopital's rule, or using the continuous function rule, we can show that this converges to 1. So this is equal to our c, which is greater than 0. And so by part A, since the B series, since B diverges, the A series has to diverge. Okay. Let's look at one involving geometric series. I haven't given you one of those yet, so let's call this example 2. So now let's let our A series be this. And of course, the obvious thing to compare it to is the geometric series, where r is 1/2. So this will be our series we want to compare it to. And we know that this converges. But again, when we try to use the direct comparison test, the inequality is the wrong way. So if we try the direct comparison, notice that we need to have an less than or equal to bn, but we don't have that. Okay, this condition is not satisfied. So we cannot use the direct comparison test, but we can use the limit comparison test. I'm going to go ahead, I'm going to take the ratio. It doesn't actually matter, well, okay, I'll do it in the right order. As long as we're careful, it really wouldn't matter. But when we look at the ratio of an over bn, this is going to be the limit as n goes to infinity of 2 to the nth over 2 to the nth minus 1/2. And again, we see that's going to go to 1. This is our c, which is greater than 0. Okay, so again, by part A, since we know that B converges, it follows that A converges also. Okay, so those are two nice theorems. When we have things that look like P series or look like geometric series, this will be the first two theorems that we try out.